So, good morning everyone. I'm here to talk to you about a small aspect of my PhD work, which, as Ian kindly said, is on efficient nonlinear wind blade modelling. So, brief introduction of my PhD and the topic. So, there's been a trend towards larger wind turbines, and this is because it lowers the levelized cost of energy. There's a few reasons for this, but in general, wind speeds are slightly higher and cleaner at higher altitudes, and the power generated by a disk increases with the radius of the blade squared. But what this means for us is that there's longer blades and there's more advanced technologies which pose analysis and design challenges. So, for example, long compliant blades means large deflections, which kind of pushes the boundaries of linear structural analysis. And also the design spaces become greater and the design trade-offs and decisions become more complicated. So at the University of Bristol, we've been developing a multidisciplinary analysis and optimization tool called Atom, which we think is capable of addressing these challenges. So my PhD can basically summarize with two main aims. The first is the validation of these analysis tools for large turbines, and the second is then going on to use them to assess the cost of energy benefits of aeroelastic tailored design. So aeroelastic tailoring is basically trying to exploit the aeroelastic coupling, so the coupling between the aerodynamic loads and the structural deflections. And one of the main ways of doing this, as Vincent spoke about earlier, is through bend-twist coupling. So it can either be induced by anisotropic composite materials or with geometry of the blade. So that figure on the bottom right there illustrates a swept blade. You can see the curved planform, and then the lines going across it also indicate curved fiber paths, so it's a variable stiffness structure. So what I'm mainly going to talk about in this presentation is the validation aspect of the PhD. We did a validation study of a static load test of a large turbine. So, successful design requires that we accurately predict the loads during the design phase. So that's for assessment of power and assessment of failure. But with compliant and tailored blades, as I said before, the blade deflections can be large and push the limits of linear structural analysis. So, just quickly, linear structural analysis assumes that the stiffness of the structure remains constant throughout a loading process. Nonlinear aims to predict the changing stiffness due to the changing geometry. So what we did is try to replicate a static load test from a large commercialized blade using Atom's V model. And the blade length was 83.5 meters, and it was from a 7 megawatt turbine. So this is a little figure of the test setup. The black line indicates the blade axis within the hull, so that's the undeflected position. And then the blue arrows indicate the pulleys. They're connected to load frames on the blade and then fixed to the ground. So these are the results. On the left, we have the maximum flapwise load case, and on the right, the min flapwise load case. And the dots indicate measurements, the lines indicate predictions, and the black line is the undeflected state, and the blue and red are the deflected state. So what we can see on the left is that there's a much greater difference between the linear and the non-linear predictions than on the right. So this is under the extreme loading condition, the deflections are going into this non-linear region and basically exceeding the limits of what is capable by the linear structural analysis. So this kind of highlights the necessity of non-linear structural analysis for predicting deflections, for predicting loads for these large compliant blades. So that's that, and to conclude, we've shown static load test validation of an 83.5 meter blade, linear versus non-linear structural analysis, and my ongoing future work is to go on to design a 20 megawatt turbine with bend-twist coupling within a full aeroelastic design optimization. So that's everything from me. If you've got any questions, then we're happy to answer them or find out.